In this presentation, we'll continue to talk about waves, and specifically we're going to talk about the natural frequency of vibration and resonance. So it turns out that all objects have some natural frequency of vibration. Some examples might be tuning forks. So if you were to strike a tuning fork, it creates a sound, and that sound is coming from the fact that the tongs of the tuning fork are vibrating. And so that tuning fork vibrates at its natural frequency of vibration. And different tuning forks have different natural frequencies of vibration, and therefore you can hear different tones. But basically everything has some natural frequency of vibration. If you were to tap a glass and you hear a sound, that glass is vibrating at its natural frequency of vibration. If you were to pound your hand on a table and then you hear a sound, that table is vibrating at its natural frequency of vibration. A really great example of this is if you were to try to play a wine glass. And so basically if you take a wine glass and you put some liquid in it and then you wet your finger and you move your finger around the top of the wine glass, you can cause the glass to oscillate, and it will oscillate at its natural frequency of vibration and you'll hear a sound. Now if you put different amounts of liquid, like in this picture here, different amounts of liquids in the glass, and you have different size glasses, each one of those will have their own natural frequency of vibration. So the video that I have here is a really nice video of an individual who is going to play the wine glasses, and they're going to play Ode to Joy. I'm not going to show the whole video, but I wanted to at least show part of it so that you could see how objects have a natural frequency of vibration. So it's really interesting that objects have natural frequencies of vibration, and not only do they have natural frequencies of vibration, but some objects actually have more than one natural frequency of vibration. So another example would be a spring, and a spring that has a mass on the end will vibrate at its natural frequency of oscillation when it's displaced from equilibrium. So in this particular picture, I have two different springs, and they have different spring constants. That's not really that important right now, except that when you look at these springs, you can tell that they're not exactly the same, right? So one is thicker. They are actually the same length, but when the masses are placed on them, they stretch differently because they have different stretchiness. That's probably not a good word for it, but so when I go ahead and I start this video, it will show that they oscillate at their natural frequencies, but they have different frequencies of oscillation based on the fact that they're made of different types of springs. So we can see that they are not vibrating exactly the same way, but each of them individually is vibrating at their own natural frequency of vibration. You can also force an object to vibrate at a particular frequency. So one example of that is in this particular picture there are tuning forks that are attached to a wooden chamber. And so by forcing the tuning fork to vibrate at its natural frequency, because it's attached to this wooden chamber, it forces the wooden chamber to vibrate at the same frequency as the tuning fork. And so that's forced vibration. When you force an object to vibrate at a particular frequency, that's not necessarily its own natural frequency. So let's go ahead and see if we can take a look at how this works. Each of these tuning forks have a different natural frequency, and each one of these chambers is vibrating at that separate natural frequency. And this actually causes the sound to be louder because it's causing that chamber to vibrate. Another example that you might be familiar with this is how a guitar works. So if you were to pluck a string of a guitar, it actually forces the wooden chamber of the guitar to vibrate as well, and that actually amplifies the sound. So the wooden chamber has its own natural frequency of vibration, but based on the fact that it's attached to those strings, it's going to vibrate at that frequency. Resonance is a special case of forced vibration. So, in resonance, you basically are imposing a frequency or forcing an object to vibrate at its natural frequency of vibration. So, when that happens, you can actually have some very interesting characteristics of the object. So, again, resonance is when you match the natural frequency of vibration of the object and force it to vibrate at that natural frequency. And so, some of the characteristics of resonance are that you can have very large amplitudes of the wave and of the object that's actually vibrating. And sometimes those amplitudes can be so large that the object can break. Another characteristic is that you don't need to put in a whole lot of energy in order to cause this forced vibration. And so an example of this would be breaking a wine glass. And so there's a little GIF file over here that's showing this. So this is a wine glass and there's a speaker next to it and you can kind of see the sound waves coming out. And if you adjust the speaker's frequency so that it matches the natural frequency of vibration of the wine glass, it causes that wine glass to really start to oscillate, large amplitudes of oscillation, and it can actually cause that wine glass to break. So I'm going to go ahead and throw in a reference here for those of you who are Harry Potter fans. So if you're Harry Potter fans and you've watched the Harry Potter movies, there's a scene in one of the movies where the woman that's on the painting is trying to break a wine glass with her voice. And so that actually, if you could have the right amplitude and match the right frequency of vibration, then that is a possibility that you could do that, just like a speaker. Now, obviously in the Harry Potter movies that didn't happen, but just as an example. Another example of resonance that you're probably really familiar with, which you don't even realize, is when you are pushing a child on a swing or you're pumping on the swing, to go higher and higher. What you do is when let's say a child is going back and forth on a swing, you actually push the child when the child is at their highest point, and as a result, that keeps increasing the amplitude. You don't push them at their lowest point, right? You are forcing the natural vibration of the swing. You're imposing another force to have that swing oscillate at its natural frequency of vibration. That can cause large amplitudes without putting in a whole lot of energy. There's a lot of good examples of resonance, and I'm sure if you wanted to look at that online, you could certainly find some examples. Another example that I typically talk about in class is the Tacoma Narrows Bridge. There's a video of that, lots of videos on YouTube that you could see. I'm really not going to talk much about that, but I just wanted to show a picture of it. The Tacoma Narrow Bridge was a suspension bridge in California that was built, I think it was in the early 1900s. And essentially, right after the bridge was built, because of natural vibrations in the area, the bridge started to oscillate. And so it happened that the natural vibrations in the area, whether it be winds or just natural vibrations that are occurring locally, they happen to match the natural frequency of vibration of the bridge. And this bridge is actually made of steel and cement, and you can see that it's oscillating a lot. And if you watch the video, it's much more dramatic. But essentially, the bridge, that oscillation caused the bridge to collapse. And it's really interesting to look at because the bridge was oscillating quite a lot even when it was opened and they had a parade and people went across that bridge even when it was oscillating, and they trusted that it was built correctly. Another example of sort of this idea of resonance and matching frequencies, you can demonstrate with a set of tuning forks. And so what you can do is you can strike, so I'm going to just sort of talk through this with the picture. So I have these two tuning forks. I have tuning fork A and tuning fork B. And if you strike tuning fork A, it sends out a pressure wave, a sound wave. And if the tuning fork B has the same frequency of vibration, natural frequency of vibration as tuning fork A, that pressure wave will activate the second tuning fork. And that's because of this matching of frequencies. So you don't have to have a large amplitude of a pressure wave, but just because of the fact that those two frequencies match, it causes large oscillations in the second tuning fork. And so this other animation just kind of shows a picture of how that pressure wave activates the other tuning fork. But it only works if those two tuning forks have matching frequencies. So I pulled this off of YouTube. I would normally do this demonstration in class and show it as a video or show it as a live demonstration, but I thought it would be interesting to show this. So here we have two tuning forks. They have matching frequencies. What you're going to see in the video is the individual is going to strike one of the tuning forks, and then he's going to bring a microphone over and put it near the chamber of the other tuning fork setup, and he'll put his hand over the one tuning fork to stop its vibration, and you'll be able to tell that the other tuning fork is actually vibrating. So that's another example of resonance and matching the natural frequency of an object.